is 1.1%. Okay, and generally the hydrogen, right? So the hydrogen H1 is 100%, and the deuterium H2 is its natural abundance is 0.016% here. Okay, and in nitrogen, like nitrogen N14 is the natural atom which is available in the 100% range, and its isotope, nitrogen isotope is N15, where its intensity or the availability in the earth is 0.38% here. And oxygen is O16 here, 100%, and O17 and O18 here, two isotopes for the oxygen. We can see the two isotopes here. O17 is 0.04%, very minute, okay, negligible generally, and O18 is 0.2%. Okay. And sulfur S34, sorry, S32. Okay, so it is 100%. Okay. Okay. Yes. So here you see the means the natural atom and their isotopes here and their percentages. You see the sulfur is the natural occurrence of the sulfur is a S32 here, where it is 100%, and its isotope is S33. Okay, the availability is 0.78%, and S34 is 4.4%. Right. So it is S2 is 100%, and S34 is 4.4%. And chlorine 35, Cl35 is 100%, and Cl37 is 32.5%. Okay, it carries only one isotope. Chlorine is having one isotope here with the two mass difference. Okay, with the two mass difference here. Cl35 is 100%, and Cl37 is 32.5%. Okay, and bromine is generally, yeah, the bromine 79 is 100%, and bromine 81, it's isotope with two mass difference, where the availability or the natural abundance of bromine is 98% here. So almost it is 1:1%, and chlorine is it is 3:1% here. So these are the natural atoms and their isotopes here, right? So in the compound, if that particular compound is carrying these any isotopes here, in that case you will get the our last peak for the isotopic atom here. So you cannot take it as a molecular ion here, and based on the ratios, okay, molecular ion M plus and M plus 2 isotopic peaks ratio, we can identify the which which isotopic atom is there, right? Yes. So yeah, the notation are designations for the isotopic and peaks. So you can see here the general notation M plus X here, right? So M is the molecular weight of your molecular ion, and plus 2 is the higher mass. Okay, means the M by Z of isotopic ion and molecular ion. For example, if you take chlorine, chlorine is 35, right? So chlorine 35 is a molecular ion M by Z value, and chlorine 37, right? So it is isotopic, isotopic mass here. So the difference is 2 mass. Okay, the difference is 2 units here. So we mention, or we can designate as a M+2. Okay, so here also you can see where this M plus, it is 100% molecular ion peak here, and the remaining all these are the isotopic peaks. Okay, so like 101, 102, 103, 104. So 105, 106, 107, 108. So all these are the isotopic peaks here, and the designations like M+2 or the P+2. So you can write as a M or the P. P is a parent ion. P stands for parent ion. M stands for molecular ion. Okay, so you can write any one. You can mention any one, M+2 or the P+2 here, right? So where the M+2 is 2 mass difference, and M+3 or the P+3 here, P+4, okay, P+6, P+7, P+8, or the M+8 here. So all these are the isotopic peaks, and you can see the difference in their masses with respect to your molecular ion, where the molecular ion mass is 100 here, and 101, 102, 103, 104. All these are the isotopic mass here, isotope mass. So you can see. So here the 100 mass, 100 is a molecular ion, and on the right side, okay, generally the isotopic peaks appears in the right side to your molecular ion. Okay, so the isotopic peaks never found in the left side. They will find in the right side to your molecular ion. Okay, so you can designate, or you can assign the isotopic peaks like M+2, M+4, M+6, M+5, so like that. Yeah. So here, so we'll take one example like, okay, so you take formaldehyde, HCHO. Okay, so you can calculate the right. So you can calculate the intensity or the percentage of your particular M plus peak. Right. So here the percentage of M+1 in the relative to your M plus peak here. So you can calculate, like, the 1 into 1.11. Okay, so it means here the hydrogen, its intensity, and you take the oxygen intensity, and the carbon intensity means the natural abundance. Okay, natural abundance. So carbon natural abundance is 1.11. So we take 1 into 1.11, and count the 2 hydrogens here. So 2 into 0.016. Okay, plus where the oxygen in availability or the natural abundance is 0.04. Okay, so it is 1.182, right? So roughly it is 1.1. So the presence of your M+1 peak, right? The presence of your M+1 peak intensity is 1.1. Here also, so many examples you have. And the probability for having the isotopic peaks and right, so the appearance of the signals here, you can see, for example, here where we have this okay, ethane molecule. When you are taking the ethane molecule, so ethane, CH3 here, okay, So the probability for this, okay, this is the probability having the, okay, where it is carrying the two carbons here. So both the carbons may be the C12 carbon, the normal carbon. Okay. So if both the carbons are C12, then we get the normal M3. And we have probability for one carbon is C12 and another carbon is, okay, it's isotope like C13. Okay, C12 and C13. So what is the difference here? Mass difference here, 1, right? So where C12 appears as your M plus here, and C13 it is appears as M plus 1. Okay. Or if both the carbons are with in their isotopic form, okay, both the carbons are in the isotopic carbons in the molecule, right? Then you will get the M plus 2, okay, M plus 2 peak here. So you can calculate the intensity of these M plus 2. So where the partial intensity in the ratio is here. 1 into, you see how many carbons? There are 2 carbons here, and 6 hydrogens. Right? Calculate the intensity of this. So one from the other bromine or one chlorine or 2 chlorines, then the intensity of isotopic peaks, already, you have in the, like, for example, we have the molecule with 2 chlorine atoms, right? The molecule with 1 chlorine atom, for example, right? So a molecule with 1 chlorine atoms, we have this molecular ion, right? M plus here, and M plus 2. Its intensity is 3:1 here. Okay, its intensity is 3:1, where the N1 equal to 1, right? And its percentage, natural abundance percent, A is the 1 here. Okay, and where the B is 32.5% here. Where okay, so with isotope here. So we have the intensity of this one is a 3:1. Okay, like you can substitute in the right. So A plus B whole square formula, right? So where the here the N equal to 1 only, N equal to 1, then obviously it is right. So it is 3:1, and with bromines, sorry, bromines with two chlorine atoms here. In that case, N equal to 2 here, then we will because N equal to two atoms, 2 chlorine atoms. Then you can substitute in this one. Okay, so A square plus 2AB plus B square here, right? Then A equal to 3 and B equal to 1. Okay, so you can see this. A square means like 3 square, it is 9 here. 2A equal to 3 and B equal to 1. So it is 6, and B square is a 1 square. It is 1. So if 2 chlorines are present, then we will get the molecular ion and isotopic peaks, 2 chlorine isotopic peaks, like M plus 2, M plus 4, intensities 9:6:1. Okay. And with one bromine is it is 1:1. It is two bromines there. 1:2. So like and molecule with uh, sulfur, right? So when the molecule is carrying sulfur here, so generally we'll get the intensity of, okay, so 4:1 here. Okay, so 4:1. So if you observe the 4:1 intensity, then it indicates presence of sulfur here. Okay, so these are the some to easily identify the molecular molecular and isotopic peaks here. Yes, and next the fragments. Okay, in the mass spectrum, the fragmentation appearance of that signals. Right? So each line or each signal in the mass spectrum corresponding to your fragments here. Positive, right? Cation generally. Fragments means cations only, because only we get the signals for the cations here, and molecular and cations. Okay, so now you see in this particular mass spectra, the McLaughlin fragmentation or the rearrangement is important. So McLaughlin generally the compound is carrying the gamma hydrogen, right? The compound, when it is carrying the gamma hydrogen, then it undergoes the McLaughlin rearrangement or McLaughlin fragment. So here you see this particular compound in this ketone. Okay, so here in this ketone here. So with respect to of this ketone, this is alpha, this is beta, this is gamma. So requirement for this McLaughlin is a gamma hydrogen. Okay, so if there is no gamma hydrogen, there is no McLaughlin fragmentation. So the main requirement for this McLaughlin fragmentation is presence of gamma hydrogen, and they will give right some rearrangement ions here. Right? So here you can see generally in this particular carbonyl group with the gamma hydrogen. Right? So for the formation of the molecular ion, basically we'll remove the lone pair electron, because the ionization potential IP, the IP values for various electrons is already we have discussed in the last class here. IP values. Okay, so where the n electrons, okay, non-bonded electrons, then bonded electrons here, pi electrons, then sigma electrons. This is the order of removal of electrons, right? This is the order of removal of electrons, and the ionization potential with the IP values, right? So IP values are more for the non-bonded electrons, then pi bonded electrons, then sigma bonded electrons. Okay. So what is IP value generally? Ionization potential. Ionization potential is the energy required to remove the outermost shell electrons, right? The energy required to remove the outermost shell electron is called the ionization potential. So the ionization potential is less for this n bond electrons here. Okay, so you can easily remove the electron from the electrons. And the sigma bond, because the sigma bond is strong bond. So the outermost shell is right. So where the oxygen is carrying the two lone pair electrons, so you can easily remove one electron here. And, okay. So you can generate the. So after formation of this molecular ion, So it undergoes variety of fragmentation. Okay, so where gamma hydrogen fragmentation, this fragmentation, and here the beta fragmentation. Okay, so gamma bond fragmentation are the cleavage, homolytic cleavage. Here you see only the homolytic cleavage here. Radical formation will be takes place, and the bond alpha beta bond will be going to cleave. Then what you get here? So we'll get this particular fragments here. So you can see, right? Right. So here, here radical, here you one radical, and here one radical, and here also you get one radical. So these two radical combined and forms a double bond. It is removed as a olefin here, olefin moiety. Then the other part is it is obtained as your molecular ion. This is obtained as a molecular ion. Okay. So this is molecular property rearrangement. So the requirement is gamma hydrogen. So the so we see the instrumentation of this. Okay. So instrumentation your mass spectra. So generally, it is having this kind of right. So the block diagram here. So block diagram of this mass spectra. Here is your sample. Sample general just with the principle of mass. So sample the sample is vapor state here. Only vapor state samples are the compounds are accepted in mass spectrum. Okay, so you take the molecule, so you convert its compound into vapor state. Then it 70 electron volt, 15, right? So the 70 electron volt electronic impact is applied. Then so then it undergoes ionization and it forms a molecular ion, right? And all this conversion, molecular conversion is takes place in the ionization chamber. This is your ionization chamber. Molecular further undergoes variety of fragmentation. Right? So it comes variety of fragments, and you will get this, right? So these fragments will be analyzed by the mass analyzer, right? So one more part is there to analyze the fragments. There is a mass analyzer, and that mass analyzer it analyze the fragments here, and it collects only the positive, right? Positive charged, right? Positive charged fragments, and right. So it is received by your collector, and this collector will be okay. So after collecting of that fragments, positive charged fragments here, so there is a formation of that particular, right? Formation of that signal, and generally that signal is it is denatured or deformed here, right? So your amplifier will be right? So removes all the noise if that signal is in the noise state. So your amplifier will be improve the right. So improve the that particular intensity of your signal. That is recorded. Right? So this is the way we start. So with your compound is when it is placed in this right, so sample holder. So where this solid or the liquid compound, any compound, you can take solid or the liquid here. So where this solid or the liquid compound, it is undergoing the vaporization, it converts into vapor state here, and then it is moving to your sample receiver, right? So then in this particular ionization chamber, right? So this your vapor sees it is passing to your ionization chamber, and in the ionization chamber, so we have the tungsten filament. Okay, so you can see the tungsten filament where we are applying that 70 electron volt electricity. Okay, so through this tungsten filament here, so your particular vapor state molecules at the compound, it is uh, undergoing the ionization, and it is converting into molecular ion, right? So the conversion of molecular ion takes place in the ionization chamber only. Okay, and in this ionization chamber, you have this positive poles and the negative poles here, and at this positive poles, yes, okay. So at this positive poles where it is recognized the positive ions here, right? So then you are the positive ions like cations here, so they will move from ionization chamber to the next part of your instrumentation, like analyzer here. Okay, so in the analyzer, so these positive ions are passed through this particular uh, ionization chamber into the analyzer, and this analyzer will be, right, so analyzer will recognize uh, the feasible ions, suitable ions here, and it is passed to your amplifier. So in this particular amplifier, okay, so amplifiers where the signals are modified with the original intensities here. Okay, because before the coming to this amplifier, the signals are in the random nature here, and their intensity is not corrected, right? So in the amplifier, so it will be okay. So it modify the actual original intensities, and finally it will be passed to the recorder. Okay, so recorder which is connected with your computer. So in the recorder, so where this particular uh, right, so recorder, it gives graphs for corresponding positive ions or the fragments here. Okay, so this is the instrumentation.
Sir,
Yes,
why we require double focusing in mass spectrometer?
double focus means this is high resolved spectra. Okay, double focus means it is a type of what is that? What is that? Resolved instrument. It is in advanced instrument. That's all. Double focus mass spectrometry is, it is a high resolved spectra. To get the high resolved spectra, we use that instrument. That is
Right.
advanced one only. Like for example, if you use right, so like you have like different mobiles, right? So we take the advanced version. For example, where I am using Reno 8, okay, Oppo Reno 8 here. So Reno 7, this is the before stage of that. Reno 6. So that all these are the versions. Okay, 6, 7, 8. So all these are the versions here. Apple 6, Apple 7. other, if you take the Samsung 9, okay, and Samsung 10. So all these are the versions here, and in every version you will have some features, right? Some advanced features. So like that here also, what is that, double focus mass spectrum. So it is some advanced instrumentation here. It gives more clear graph or the more clear spectra, and it gives some more information also. Okay, along with the resolution of the graph, you get some advanced what is that, some more information, right? So for example, in the basic, okay, in the basic mass spectrometry, it gives only the information about the m by z values. Okay, if you take advanced one, right, the next version of the mass spectrometry, so it gives it provides information about the uh, my m by z value as well as the isotopic values, and so some hydrogen value also sometimes it is calculated here, right? So the only that is the advanced version of that.
Right, sir. Right.
Okay. And Ayesha Fatima is the host. So if you make me co-host, then I can share the notes, because means being a co-host or the host, only host and co-host are right to share the notes here. So I am not, means that person is not make me co-host, so I am unable to share the notes actually. So Ayesha Fatima is a host here. So in the list I am seeing Ayesha Fatima. Are you there, ma? Okay, fine. Right. Now I can able to share that. Yes. Next, the presentation of mass spectrum. So how to present the mass spectrum in the 2D? Okay, so in the two-dimensional uh, plane. So how to present the mass spectrum? So you see the here in the y-axis, we'll take the percentage of natural abundance or the relative abundance. Both are same. Natural abundance or the relative abundance. So on y-axis, we'll take the natural abundance here, and on x-axis, we'll take the m by z values here. Mass by charge. M by z means mass by charge values here. So this is the presentation of your graph. And types of mass spectrum peaks. This is very, very important. Types of mass spectrum peaks here. So we have variety of means we will observe the variety of peaks in the mass spectrum, where the molecular ion peak, fragment ion peak, isotopic peak, metastable peak, and base peak here. These are the some notations, are the some terminology which we means we'll get means we'll have the in the mass spectrum, right? So molecular ion peak, or you aware of that molecular ion peak here. So molecular peak nothing but where m by z, right? With this basic when the one electron is removed from the vapor state molecule. So when it is losing the one electron, then it converts into molecular ion. That is a molecular ion peak here. And fragment ion peak. Fragment ion peak means variety of fragments like m by z 90, m 92, m by z like right. So 64, m by z yeah 35. So all these are 43 like that. So whatever that line sees appear, that is a fragment ion peak one. And isotopic peak generally. So isotopic peak is where the higher mass value peak, higher mass value than your molecular ion, which is appears in the right side to your molecular ion, right? And metastable peaks. So sometimes what happens here, right? So that particular, right? So molecular ion, right? So after molecular ion, you will get, yes,
Odd and even fragmentation, sir.
odd and even.
Frag Fragments, sir. Fragments.
Hmm.
How will sir justify the odd and even fragments?
Odd and even fragmentation, that is based on the mass molecular weight only, right? For example, here the molecular weight is 92. You take 92 here, right? So mass m by z is 92 here. Okay. So right. So it's 92. It is a even number, even mass, right? And odd and even. Okay. So actually, odd and even is like you see, this is the molecule, right? So this is the molecule here. When it is 70 electron volt, electronic impact is applied, then it is converting into molecular ion. Then it is undergoing the, right, fragmentation here, and it gives C. So here this molecular ion, right? So it may be undergoes the homolysis or the heterolysis, right? Homolysis or the heterolysis. So if it undergoes the homolysis, right, then that is called the even, okay, even fragmentation. If undergoes the heterolysis, then it is odd fragmentation. That is odd even fragmentation, nothing but means the bond cleavage, right? So the fashion of bond cleavage, fashion of bond cleavage here, whether it is following homolytic cleavage or heterolytic cleavage here, right? That's a homolysis, homolytic. Sorry, what is it? Homolysis fragmentation or the odd fragmentation. After getting the fragment, its mass is even. That fragment mass is even number. Then it is even fragmentation. After fragmentation, the formed fragment mass is odd. Then you can name it as a odd fragmentation. That's all. Yes. So here is a fragment, various peaks appeared in the mass spectrum. Isotopic peaks and metastable peaks and base peak. So generally base peak, what is base peak here? The highest intense peak is the mass spectrum is a base peak, whose intensity is 100%, right? Whose intensity is 100% is called the base peak here. Right. So you can see here the molecular ion, already you know that molecular ion with upon removal of electron, right, in the vapor state to form the ion is a molecular ion, and fragment ion peaks. So all these are the fragment ion peaks you can see. So when this particular molecular ion is undergoing the further fragmentation, we are getting all these m plus m, okay, m plus 2 here, m plus 3. So all these are the fragment ions. And the presentation, you can see it here, the mass graph, right? So fragment ions. And that fragment ion, you can see the difference in the mass. For example, one, right, molecule is there. You take propyl group here, propane, CS3, CH2 CH3. Okay, so when it is undergoing the fragmentation, right? So just this is your malcrayon. Then we get the CH3 CH2 plus sorry. Okay, and you get the CH3 plus, right? So CH3 plus, it is 15. So propane mass is how much it is? C3H6 8 C3H8. How much mass here? 3 is 312. How much it is? 24 plus 8. How much it is? 8 32. Right. So the mass is molecular ion mass is a 32 here. And after removal of this CS3, so where the 15 unit 12 plus 3 15 units removal takes place. So 32 minus 15 here. So it is sorry, so C3 is 6 8 H8. How much mass? 36, right? 36 plus 8. It is 14 44, right? So it is 44. So first you remove the sequentially, you can remove the methyl groups here. So first you remove the CS3 group. Then how much it is? 44 minus 15. So it becomes 30, 29, right? 29, 15, 30, 40, yes, 29, right? So you will get mass spectrum, but here the 44, one line for 44, one line for the 29 here, and one signal for 15, right? So for propane, N-propane here, so you will get these fragments. So all these are called the fragment ions, right? Fragment ions. Next, isotopic ions peaks. So isotopic ion peaks, the presentation of this isotopic ion peaks is in right side area. You can see this is these are the fragment ions here. Right. So these are the fragment ions, and this is your molecular ion. And the right side, okay, on left side the fragment ion. On right side, you can see the isotopic ions here. Right. And with their intensities, you can recognize or you can identify the presence of the number here. For example, one chlorine is there. So you can assume presence of one means the intensity of the M plus and M plus 2 is 3:1. And for 2 chlorine, 9 is 6:1 here. Here you can see the presentation of that graph, appearance of the graph here. If with this is with 1 chlorine, and this is with 2 chlorine here, right? So you can see this is the here the 9:6:1. The intensity ratio is 9:6:1 here, right? So the appearance of the graph is like this. This is molecular ion, and on right side you can see the two isotopic peaks like M plus 2, M plus 4. Okay, and you can see the difference in their intensities. And here the bromine, right? So for bromine, here one bromine, generally 1:1 ratio, and with the two bromines here, 1:2:1. Right? So you see this difference where the left side means molecular ion and the M plus 4 peaks are equal, and the middle M plus 2 peak height is it is double to that molecular ion here. Okay, so like that. So based on their intensities, you can have the idea about that isotopic atom. And metastable ion peak here, metastable peak. generally here the metastable peaks, these are the very low intense peaks here. These are very low intense peaks, and these peaks are obtained by the appearance metastable peak. It is broad peak in the mass spectrum. If you get any broadness here, right? So any broad peak, so that is corresponding to your metastable ion. Okay, and this metastable ion peak is, and generally it is not common peak here, right? It is very right, rare peak. Metastable peak is a very rare peak here, and it is calculated, identified by, right? So where it's for example here, right? So it is a difference of your, okay, so it is difference of m plus 4 minus m plus 2 by 2. Okay, so m plus 4 minus m plus 2 by 4, sorry, 2 here. So the difference of the two isotopic peak, right, so is called the metastable ion peak. And generally this, it is broad peak here, and it is very diffuse. Diffuse means like you see this kind of the broadness here, and very low intense peak. And the base peak, it is higher, most highest intense peak in the mass spectrum. Okay. So mass spectral pathways. So you can see the, I mean, so pathways here, fragmentation pathways. Here is a molecular ion. Okay, so molecular ion with the odd electron. Okay, molecular ion with the odd electron. So after fragmentation, okay, there is a molecular ion A plus, okay, AB plus here. Right, so this is your molecular ion. So it is undergoing the fragmentation, and it is giving the, right, so even electrons fragment and odd electron fragment. Right, so odd electron generally the single electron radical. Right, radical, free radical is a odd electron species. Right? The even electron, right? So because it is odd electron molecular ion. For example, your molecular ion is, right, even electron. Right? So then it is undergoing a fragmentation, and it gives a even or even. Means here, what is happening here? So where it is, this is your neutral molecule. Here in first case one, you get the both the ions, means both are what is that uh, reagents here, right? Here we got here the cation and the free radical. Both are the unstable species only. Okay, and again same, where the molecular ion is with odd electron here. Molecular ion is odd electron. Then we'll get here odd electron molecular ion and even electron neutral ion. So how you get the neutral ion generally? By taking the electron. Right? So here is, it is losing the electron here. By losing the electron, it is converting into molecular ion. Right? So this molecular ion, so it will take one electron and it is converting into neutral ion, means neutral molecule. So it becomes even electron, because here it is odd electron, it is adding one more electron, so it becomes even. That is one pathway. These are the possible pathways only, right? And here is molecular ion with even electron. So with even electron, so where you see AB, right? So it undergoes the fragmentation, and A will be obtained as a even electron species, and B is also obtained as a even electron species, but it is neutral one, right? So it, by gaining the electron, it is converting into even electron species here. That is the possible pathways. Okay? Here we can see this pathway with one example. Okay, so here is we are taking this benzene here. Okay, we are taking the benzene, generally the benzene with the odd electron. Okay, benzene with the odd electron. So this odd electron benzene, it is undergoing the fragmentation by losing the hydrogen radical. Generally hydrogen radical, free radical, it is odd electron species. And because it is odd electron, right? So if it lose one electron, so it becomes even electron. So we got this phenyl radical, okay, phenyl cation, sorry, phenyl cation with even electron and hydrogen free radical, right? Phenyl cation with even electron and hydrogen free radical. And here is toluene, okay. So toluene with odd electron, right? Because the toluene molecular weight is 93, I think, right? So it is 93, so it is odd electron. And this molecular ion is undergoing the fragmentation. So by losing the proton, right, hydrogen radical, so it is converting into benzyl cation, right? So benzyl cation, it is right, so even electron, and hydrogen radical, it is odd electron, right? And you can take this allyl, right? So allyl molecule, right? So this allyl molecule is also undergoing the fragmentation. We are getting this particular even electron allyl carbocation and methyl radical with your odd electron, right? So these are the pathways here. And yes, here we can take the propylium cation, right? So here is a propylium cation with even electron. Okay, so this propylium cation, it is undergoing the fragmentation, right? So in the propylium cation, where two homolytic cleavages takes place, and by removal of what is this double bond, means C2H2. Okay, so removal of two carbons and two hydrogens here, right? So we got this particular, so where this radical is forming bond and it is converting into cyclopentadiene cation here, cyclopentadiene carbocation, and other part is removed as your acetylene. Okay, acetylene and cyclopentadiene cation, okay, where the cyclopentadiene is with even electron, and this particular acetylene is also with even electron. Okay? So that is a pathway, the presentation of pathway here. Yes. Now the fragmentation rule. So fragmentation rule means how to do the fragmentation, and means it guides us. Okay, this fragmentation rules guides us to do the fragmentation, and how to recognize, right? How to recognize the fragment ions here. So here you see which bond. Okay, which bond you need to do the cleave, means which bond you need to break, right? Okay. So here, for example, in a straight chain alkanes, successive loss of methylene group are 14 unit characteristic fragmentation, right? So fragmentation rules, this is important here. So in a straight chain alkanes, if you have the straight chain alkane here, so sequential removal of the methyl groups here, sequential removal of methyl group is suitable fragmentation, right? For example, here you see 1, 2, 3, 4, 5. This is the pentane. N pentane is there. Okay, here is a N pentane. So in the N pentane, there are 5 carbons. So, for example, if you cleave here, then you get the propane and ethane. So this is not allowed. This is not a suitable or the correct way of fragmentation. So sequentially you have to remove. First you remove this methyl, then you remove this one, then you remove this one, then you remove this one. So this is the sequential removal of methylene. Methylene are the 14 unit here, because CH2, right? CH2 is 14, C 12 plus 2, 14, right? So sequential removal of 14 unit is a correct pathway, right? So here you can see with the electron impact. So first we have removed this methyl group here, then its molecular weight is 72. Okay, and again we remove this particular so actually we removed one electron, and we are converting this into molecular ion. Then we remove the methyl here. Okay, methyl radical, free radical, and butane carbocation. And butane carbocation, its molecular weight is 57. Then you remove the C, then it becomes 43. Again you remove the CS2, again 14 units, then it becomes 29. Again you remove the next CS2, 14 unit, then you get the 15. So this pathway is allowed, right? So the removal of the 2 carbons at a time is not means suitable pathway here, right? So here when you remove in this manner, so it is easy to, okay, then it is easy to recognize the fragment ions here. So here you see all the fragment ions with 15 mass, 14 mass difference. 14 mass difference here. You can see 72 is a molecular ion, right? So this 72 is a molecular ion here. And with 15 mass difference, C4H7, sorry, C4H9, it is 57. Again, 14 mass difference. We got here, C3H7. Again, with this 14 mass difference, we got the 29 people for this style carbon. Again, with the 14 mass difference, we got this methyl carbon. So, sequential successive removal of 14 mass is allowed, and it is suitable. And if the branch, okay, so when the molecule is state chain, you must follow this. And if that particular right? So in a branched alkanes, fragmentation of highly branched position. Right? And the outgoing, right, outgoing radical, usually long chain radical. Right? So for a molecule here, so we have to, okay, so remove the, right, you have to do the mutation in order to get the branched, okay, highly branched yes, in a branched alkene, the fragmentation of highly branched position and outgoing usually the carbon chain radical. Okay, here you see this is the particular where this 2,2 dimethyl butane here. So here the possibility for the cleavage, right? So you can cleave here, you can cleave here, you can cleave here. These are the possibilities, three possibilities. This is A, this is B, this is C. So there are three possibilities. But you see that the particular fragment, right? The fragment after the fragmentation, the fragment obtained must be highly branched one. Okay, the fragment in cation, right? The fragment carrying the positive charge must be highly branched one here. So here, when you do this fragmentation here, so here we got this particular isobutyl. Okay, sorry, 1, 2, 3. Tertiary butyl here, right? So tertiary butyl group. So tertiary butyl carbocation with M/Z57, and one more radical is ethyl radical. Right. So here that particular cation obtained in this fragmentation, right? So it is highly branched one. So it is okay. So tri-substituted. So this is allowed. If, for example, if you do this fragmentation here, right? So if you do the if you remove this methyl, then you get the right primary carbocation, right? So for example, if you remove this methyl, then you get some heterolysis. So you get this CS2 plus. So this is primary carbocation. And if you remove here, so this is tertiary carbocation. Right? So generally, the stability of carbocation is tertiary carbocation, then secondary, then primary. This is the stability of carbocation. So after fragmentation, okay, the formed cation must be stable one. And the third rule in cycloalkanes, so loss of neutral ethene, loss of neutral ethene is characteristic fragmentation. This is also one of the important fragmentation here. So in the cycloalkanes here, the loss of neutral ethene, neutral olefin here, ethene nothing but this one. This is ethene. Okay, ethylene. So in the cyclic compound, cycloalkanes here, the loss of ethylene is a characteristic fragmentation here. Right here you see where the right, so this is cyclohexane. So where by removing one electron from any one, because it is symmetrical one, so you can remove the electron from any of the sigma bond, because there is no pi bond and n bond here. So sigma bond removal of electron from the sigma bond is takes place here, and we got this molecular ion here plus radical, right? So then after this we are going to do the further fragmentation. Upon fragmentation, okay, so we are getting this, right? So here the bond with here is a radical, and it is moved as a olefin bond, and it is becoming radical or the parent molecular ion, right? And molecular ion and the ethylene neutral one, ethylene fragment means ethylene molecule as a neutral one, right? This. So the remaining rules we'll see in the next class. So I'm stopping here. Tomorrow we'll discuss the remaining part.